So let me introduce our distinguished speaker today, Professor Ulrik Andersen from Technical University of Denmark. I know Ulrik for, well, I would say more than 10 years by now. And we met at conferences and typically at the laser physics conference. And he has always been the promising young researcher that produced wonderful results at those conferences. He's an expert on continuous variable quantum optics. And today he's going to talk about, Ulrik has got one of the biggest prize in Denmark, I think. If I'm not mistaken, it's some elite Faust or something. You might want to correct me. A prize that's awarded by the government of Denmark. So today he's going to talk about optical quantum computing with continuous variables. And I think the floor is yours. Ulrik, you can start as soon as you're ready.
Yes, I'm ready now. And thank you so much for this kind introduction, and thanks for the invitation. So I'm very delighted to give a presentation about some of our recent research. Most of it has been carried out the last couple of years. Of course, I would have been happy to visit you in Singapore. I've never been to Singapore visiting you, so maybe next time. But due to the situations, of course, it has to be virtual.
Yes.
The presentation. Okay, so as you just heard, my name is Ulrik Andersen, and I'm from DTU, the Technical University of Denmark, and I'm heading a center that we call the Center for Macroscopic Quantum States, Big Q, supported by the Danish National Research Foundation. And they've been supporting, for example, research in developing quantum computing technologies. This is also what I will be talking about today, namely optical quantum computing with the continuous variables. So we know that there are a number of different platforms for quantum computing. So two of them are shown here, but of course, there are many other platforms, but probably maybe the two front-running, or two of the front-running technologies are shown here. So namely the superconducting platform, for example, the one from Google as shown here, where they had this nice results a few years ago on demonstrating quantum advantage using a sampling algorithm, as well as the photonic platform, where they also managed to show quantum advantage last year at the USTC in China. And this experiment has actually been upgraded, recently published in Physical Review Letters. So I think in this first experiment that we see here on the picture, they had around 50 squeezed states. I mean, they're using an algorithm called Gaussian boson sampling, by which you need squeezed states. And here they built 50 squeezed states, whereas in the newer one, they have about 100 squeezed states. So these experiments are really beautiful, have really been advancing the field, but there are of course also shortcomings here. I mean, so one of them is the algorithm that they're implementing. So this is a sampling algorithm, and they do not really have any, or we do not know whether they have any applications. I mean, the one from China is the algorithm, as I already mentioned, is a Gaussian boson sampling algorithm, where we are sampling the photon numbers at the output of a linear network. But in this particular experiment here, the linear network was not configurable. You cannot change the control of the linear network, so therefore it does not have any direct applications. And also another shortcoming with these two experiments is that they're not scalable. So for example, in the Google experiment, they need a BNC cable per qubit, cooled down to millikelvin temperatures, I mean, inside a dilution fridge. So if you need 1 million qubits, which you'll need at the end of the day to make a universal fault-tolerant quantum computer, then the system simply becomes too large. So it's not scalable. And that's the same for the system in China, which is based on free space optics. and obviously this is also not scalable if you need 1 million qubits one day. So these experiments were beautiful, but there are, of course, still significant challenges in scaling this up to universal fault-tolerant computing. So what we are focusing on is on photonic quantum computing. And why do we do this? Because there are a number of advantages of using photonic quantum computing, and probably the most obvious advantages are listed here. So the first one is that most of the experiment is conducted at room temperature. Actually, the experiment I will be presenting today is only at room temperature. But if you want to do universal quantum computing, you might need some fridges, but maybe it's only for the detectors. The actual sources, the actual quantum processing unit, will be operating entirely at room temperature. So it's only the photon counting detectors that today have to be cooled down to low temperatures, but maybe not in the future. And also using a photonics system, it is scalable, potentially scalable, as you will also see in my talk, how we managed to scale up our system using time multiplexing. And one of the great advantages of using photonic approach to computing is that it's network compatible. It is fairly straightforward to combine different modules, computing modules, because most of the experiments on photonic quantum computing is at the telecom wavelength, a 1550 nanometer wavelength, which means that you can easily transfer quantum information from one computing module to another computing module. So this also gives rise to better scalability. So these are the advantages, but of course, there's no free lunch. There are also huge challenges using the photonic approach. I mean, for example, the photonic qubits they're flying. So flying with the speed of light, so they're very short-lived. When you measure them with a detector, I mean, they simply disappear, which is of course a difference to the solid-state qubits that are static, not flying, and they are long-lived. And you can perform many gates operations on them before they decohere. And also photonic qubits are not really interacting that well. So, but there are actually ways around this, this is the approach that is often taken when dealing with photonic quantum computing, namely to use a measurement-based quantum computing approach, because then we're circumventing the fact that the photonic qubits are short-lived. Because I mean, it's fine they're short-lived when you're using a measurement-based approach. Okay, so just quickly, I mean, what is the difference between a gate-based and a measurement-based quantum computing approach? So this is like what you see in a textbook when you read about quantum computing. So this is the standard gate model of quantum computation. And you're probably all familiar with this. So you have some input quantum bits, qubits, initialized in some states, could be in eigenstates, or it could also be in superposition states, as seen here, injected into your circuit, and your circuit then is then comprised of different gates. I mean, there are single mode gates, and there are also two mode gates. And then you implement your algorithm in those gates, and then by the end of the day, you need to get some data out, and this is done by performing a measurement. So this is the standard gate model of quantum computing. So the other approach I was referring to, the measurement-based approach, is quite different. So here you start by setting up an array of qubits, and this array can be in space, or it can be in time, or in frequency modes, or in different frequency modes in which you encode or initializing qubits. And then at the edge, you also initialize your input states. I mean, those states on which you want to perform computation. Now you want to link all these nodes, and this is done through entangling operations, or control C operation, by which you simply link the different nodes. So you simply perform control Z operation between all these nodes, thereby ending up with this massive entangled state. So all the qubits are now entangled, also entangled to the input state. This is called the cluster state. And now the idea is just to perform measurement on this cluster state, and through those measurements you actually execute gates. So for example, you perform measurements on your set of input states, and through those measurements you implement a certain gate, and the input state is then transformed to another node in your cluster through that measurement. Now if you want to make another set of gates, you perform another set of measurements. So now you measure these 5 nodes by which you implement gates, operations, computations on these 5 nodes, and the output is then shifted one to the left, and the output is now residing at those 5 qubits. And then you simply go on throughout your cluster state, and then at the end of the day you have an output state which has been computed. So this is quite different from the gate-based model. So again, for the cluster state model or measurement-based model, you set up a cluster state, and then you perform measurement of that cluster state on which you execute your computation. Okay, so so here again we have these 2 models: the gate-based model and the measurement approach. So the challenge with the gate-based model is to implement coherent high-fidelity qubit operations. This is the big challenge that people are facing in the gate-based model. But this challenge has now been shifted to another challenge, namely to generate a large cluster state. Because I mean, if we can generate this large cluster state, then it's actually an easy task to implement the gates, I mean, through measurements. And as I already mentioned, I mean, photonic qubits are actually suitable for the measurement approach because they're simplifying. So I mean, actually, when you're generating a cluster state, then it's being generated, and at the same time you perform measurements. So you perform a measurement right after it has been. I mean, you generate a line of qubits, and then you perform measurements, and then generate the next line of qubits, perform measurements. So you simply generate your state while performing the measurements. So that means that it's fine that the photons are short-lived. Okay, we are not dealing with qubits in our laboratory, so we use a different approach called continuous variables. So we encode information into the continuous variables of a light field, the amplitude and the phase quadratures. And in that case, the nodes, I mean the qubit nodes, are just replaced by squeeze states. So these are our qubits, and the control NOT operation between 2 neighboring squeeze states or qubits are just beam splitters. And the measurement that we're performing in our cluster is a homodyne detection system or homodyne measurements. So just briefly, what is a squeeze state? I presume that most of you know what a squeeze state is, but it's illustrated here in phase space, where we are plotting the amplitude quadrature and the phase quadrature versus the probability of attaining a certain measurement outcome. It's called the Wigner function, or there is a quasi-probability distribution. So the probability distribution for a vacuum state is just a circular Gaussian centered at the center of phase space. And now if you squeeze this Gaussian state, then you get a squeeze state as shown here. So that means that the uncertainty in the phase quadrature is lower than what you have in a vacuum state, whereas the uncertainty in the amplitude quadrature is larger than in a vacuum state. So this is called anti-squeezing. And if you perform measurement of these quadratures, and you perform measurement of these quadratures using a homodyne detection system, as illustrated down here in the right corner. So here you're simply mixing your input state, the nodes, I mean, for example, the nodes in your cluster state with a local oscillator. And you can control the phase of this local oscillator. And depending on the phase of this local oscillator, you're measuring different quadratures in phase space. So for example, you can measure the amplitude quadrature, you can measure the phase quadrature or any other quadrature in between just by controlling the phase of your local oscillator. And then after the beam splitter, you perform intensity measurements, and you create the difference currents, and in this different currents you get information about the quadratures. And one quadrature measurement is shown here. So this is a quadrature measurement as a function of the phase of the local oscillator. So at some phases you measure a lot of noise. This is the anti-squeezing, so that corresponds to measuring the amplitude quadrature of this squeezed vacuum. And then at other phases you measure squeezing at this position here, which corresponds to measuring the phase quadrature of this squeezed vacuum state. Okay. Yeah, and as I already mentioned, I mean, the way that we're entangling different nodes in our cluster state is just to interfere two squeeze states on a 50-50 beam splitter, and this is shown here. So you have one squeeze state, another squeeze state, you interfere them on a beam splitter, and what comes out is what is called the two-mode squeeze state, also called the continuous variable EPR state. And in that EPR state, we have amplitude and phase quadrature correlations. So that means that if we measure the amplitude quadrature of the upper beam, then we can determine the amplitude quadrature value of the lower beam with very high precision, or beyond what is possible using just classical methods. And also, if you measure the phase quadrature of the upper beam, then you can also determine the phase quadrature of the lower beam with high certainty. And this is just called two-mode squeezing, or entangled or continuous variable entangled states. Okay, so so now I have explained how to actually generate this cluster state. But now let's have a look at how to implement a gate in this cluster state computation approach. And therefore, I'll just be considering one link here. How to so we have one input state, which is then encoded into our cluster state, and how do we actually implement a gate through measurements. So let me just look at one single link, and that's what I have here. So just one link in our cluster state. This is my input state. The green dot here is the input state, and the two other dots are a two-mode squeeze states. One part of our cluster state. And now the idea is to entangle our input state with our cluster state, and this is done through a beam splitting operation, which is marked by this red arrow here. And then we perform measurements of this node and this node, and by doing this, we transform our input state into this node here. So this will then be our output state through which we have implemented a gate. And this is the process of teleportation, basically. And this is shown here. So this is the teleportation circuit. So this is not just another, a bit more elaborate way of illustrating this much simpler picture over here. So these two nodes is basically a two-mode squeeze state. So we have a box producing two-mode squeeze state. As I already mentioned, this is produced by mixing two squeeze beams on a beam splitter. And out comes just a single link in our cluster state, a two-mode squeeze state. And now we interfere one half of the two-mode squeeze states with our input state. So our input state is the green dot here. It's just an arbitrary state. So this is mixed with one half of the two-mode squeeze state on a beam splitter, on the 50-50 beam splitter, with the red arrow here, also the red arrow over here. We perform homodyne measurements on the two output modes, where we can control the phases of the local oscillators θ1 and θ2. And then by doing this, we transform the input state into an output state. And this is now transformed in such a way that we apply a unitary transformation onto it. So we perform a gate operation onto it. And it really depends on the measurement settings of the local oscillator, of the homodyne detectors, what unitary transformation we are performing. So yeah, just a reminder, this is the homodyne detector. So each of these two detectors are homodyne detectors, and I already explained this on the previous slide, that this is with a local oscillator, and we can control the phase of the local oscillator and measure any quadrature projections in phase space. So, and by doing this, we can perform this unitary transformation in this is called the teleportation circuit, and in this teleportation circuit, we can implement this unitary transformations, apply this to the input state. And this is a combination of a rotation gate. So this is rotating our phase or our state in phase space, a squeezing gate. So we're squeezing the the state in phase space, and another rotation gate, where these angles here, theta plus and theta minus, are given by the sum or the difference of the two measurement angles of the two homodyne detectors. It should be theta 2 here, not theta 1. Okay, so that means that by controlling the phases of the local oscillator in this measurement here, we can simply tune the unitary transformation. So we can simply implement many different, or actually an arbitrary single mode unitary transformation onto our input state just by controlling the phases of the local oscillator. We're not changing the cluster state or the two-mode squeeze state. The only thing we're changing is the measurement setting. So one example, a very simple example, if the measurement, or if the two angles are measuring conjugated quadratures, x and p quadratures, I mean projecting onto the amplitude or the phase quadrature axis, then this unitary transformation here just end up being identity. And this is what we know as standard teleportation. So you simply have your input state is equal to your output state. But for any other angles of the local oscillators, it's not identity, it's another transformation that we perform. And this is simply the essence of gate transformation in a cluster state. But this was, of course, just a single link. I mean, then we can add another step. So we have a bit more complicated cluster state now consisting of 4 nodes that will then be combined with the input state via a beam splitting operation, another beam splitting operation, another beam splitting operation. No, sorry, just one beam splitting operation here. I mean, they're already coupled via beam splitters. And then we perform a measurement on the first 4 nodes by which we get an output state. So that means that we have performed 2 single mode gates. So this was similar to what we saw before. I mean, there's a certain single teleportation circuit, and then we simply combine this with another teleportation circuit like this. And this gives us an output state, which is now transformed according to these 2 transformations. And of course, we can continue with the many single mode gates. For example, here, and this will then end up with the 1D computation. So you have an input state, you have a several teleportation steps throughout your cluster states, and then at the end of the day, you have your computed output. But this is, of course, only a single mode computation, which you can do with a 1D cluster state. But if you increase this to a 2D cluster state, then of course you can also perform multi-mode computation. So these computations of multi-mode or of 2-mode computation are also teleportation circuits, but they're a bit more complicated teleportation circuits. Yeah. So here you also just have a row of input states. You perform measurement of the next row and the next row, and then you simply perform your computation throughout your cluster state. So this is the idea of measurement-based computation in a continuous variable setting. So this is the outline of the rest of my talk. I know I'm halfway through my talk, but so just to settle what I'll be talking about from now on. So now I'll be talking about what we actually implemented in our laboratory. First, I will tell you how we actually generate a cluster state with many nodes, and then I will present some results on implementing gates in our cluster state through measurements. And then at the end of my talk, I will briefly mention how to attain universality and fault tolerance, something we did not do yet, but these are some theoretical estimations on what it takes to get to fault tolerant to quantum computing. Okay, so cluster state generation. So I already mentioned that the way to generate these different nodes is to interfere 2 squeezed beams on a beam splitter to make a single node. If you want to make 4 nodes connected, then you need 4 squeezes and 3 beam splitters. And you can of course imagine that this will not scale if these different squeezes are spatially separated squeezes using bulk or free space optics. Then this will simply be a no-go, because I mean, to do real universal quantum computing and fault tolerance computing, you will need millions of these squeeze light sources. So when you have n nodes in your cluster state, you need n squeezes and you also need n detectors. So therefore, this does not scale that well, not using free space optics. So therefore, instead of using this spatial multiplexing as shown on the slide here, we decided to use the temporal multiplexing because, I mean, the different squeeze state can also be produced at different times. And the different nodes in our cluster state can be representing different times. Doesn't have to be different space points, but it can also be at different times. It can also be at different frequency modes. But we are focusing on time multiplexing. Now I present the way that we have been producing a 2D cluster state using time multiplexing. So the work was published a few years ago, and I should point out that the lead author, Mikkel Larsen, who was a PhD student in my group at that time, and he really did most of the work that I'm going to present now. So start by producing squeezed beams, squeezed pulses of light using optical parametric oscillators. I mean, this is standard technology. So we know today that we can produce very nice squeezed and highly squeezed states using optical parametric oscillators. This was then injected into fibers, and we interfere two squeezed beams on a 50-50 beam splitter. And by now, you know that by interfering them on a beam splitter, we are creating these two-mode squeeze states or EPR states. So one link in our cluster state. And these individual links need to be coupled. And this is done by delaying one of the arms in this Maxenian interferometer with respect to the other one by exactly one clock cycle. And then interfering them again in a beam splitter. And it's important that this is one clock cycle. So you're delaying this lower mode here by one clock cycle with respect to the other mode, and they are then time synchronized on the second beam splitter. And the graph states, or the cluster state you're producing that way, is that, yeah, because of the second beam splitter BS2, you're now creating new entangling links, as shown in this graph states below here. And remember, these are different times that we're doing this. So that gives us what is a 1D cluster state. And actually, with this 1D cluster state, we could implement unitary, or we can implement different Gaussian single mode transformations using the teleportation approach that I just mentioned before. But since we also want to do two-mode operations or multi-mode operations, then we need to go to 2 dimensions. So, and this is done by delaying the mode once again, one of the modes with respect to the other one, with n times the clock cycle, and let them interfere again. And the way to illustrate this is to roll it into a cylinder, as shown here, and then we are combining the nodes again with another beam splitter, BS3, and thereby creating new links. So you can see you have many entangling links here. So I mean, the cluster state is not as nice and squared as the one you saw on the previous slide, but we do have a cluster state that can be used for quantum computation. We actually do have too many links here, but those links can actually be removed again through measurements, which I will come back to soon. Okay. And then at the end of the day, we simply perform homodynamic measurements. And for this first experiment, the homodynamic measurement was done just to verify that indeed we are producing a cluster state, a multi-partite entangled state. And in order to verify that we do have entanglement in our system, that we have a non-separable states, an entangled state, is to measure what we call nullifiers. So a nullifier for a simple two-mode squeeze state, an EPR state, is just the sum of the quadratures and the difference of the phase quadratures of the two modes. So this is one way. I mean, you have to measure the amplitude quadratures of the two beams and the phase quadratures of the two beams in order to verify that indeed we do have the correlations, or we do have entanglement in the system. The nullifiers for this 2D cluster state are much more complicated. So this is a superposition of 8 different quadratures at 8 different nodes in our states. I mean, this is here we have dived into our 2D cluster state, and then we have to measure 8 different nodes and look at the correlation between those 8 different nodes. So we measure the amplitude quadratures, set up this nullifier, and we measure the phase quadrature, setting up these other nullifiers. And the variance of these nullifiers has to go below a certain threshold in order to verify that we indeed have produced an entangled state, and that there are no bipartitioning in the state. So to ensure that there are no bipartitioning in the state, we have to make sure that the variance is below -3 dB. So we need to have more than 3 dB of squeezing in those nullifiers in order to make sure that that is generally entangled, that there are no bipartitioning in our entangled state. And we see that measuring the two nullifiers, we are indeed below the threshold of -3 dB. So these are measuring the nullifiers at different temporal mode indexes throughout the cluster. So every single dot here corresponds to a combination of 4 nodes in our cluster state. And then we shift the 4 nodes and perform another measurement. And we simply shift it throughout the cluster state. And our record is to entangle 30,000 modes. And it's simply limited by the phase instability of our system. If we had a strongly phase stable system, I mean, then we just could continue producing our entangled state. So we will be able to generate millions of entangled modes in our cluster state. Let me just take you briefly through the lab. So this is a setup or a photo of our squeezed light generator. So it's a bow tie shaped cavity with a nonlinear crystal. It's a periodically poled KTP crystal, which is being used for the squeezed light generation process, and it is boosted by the cavity. So this is done with the big and bulky and free space optics, but right after the two squeezed light has been generated, it is injected into a fiber. So the rest of the experiment takes place in a fiber. So the blue part up here, so it's all in fibers. And this is what you see here. So we have 2 delay lines. So the short delay lines, 1 clock cycle, which is lying right here. This is 50 meters. The long delay line, which actually determines the size of our cluster state. I mean, the circumference of the cylindrical cluster state is decided here. So what we have chosen n to be 12. So we have 12 modes on the input state. And that gives us a delay line of 600 meters, which is in this box here. And right after the delay lines and all the beam splitters, we injected into 2 detectors, homeland detectors, which are these 2 boxes here. And we characterize the system. I should also mention that we are not the only one making cluster states. So there's a work from the group of Akira Furukawa from Tokyo University, where they produced a similar cluster state. And their result was published in the same issue of Science as our result. So the outcome is basically the same, but they use a different architecture for the setup. So they, for example, use 4 squeeze beams and 4 detectors instead of our setup, making use of just 2 squeezes and 2 detectors. But otherwise, the performance of the 2 systems were the same. You can also generate cluster states in different degrees of freedom, as I already mentioned. So in the frequency degree of freedom, for example, and this has been done in the group of Nicola Traps from Sorbonne University, as well as the group of Oliver Pfister from the US. Okay, so our next approach is, our next experiment was to implement gates in our, sorry, I just need to, so the, our next experiment was to implement computation or gates in our 2D cluster state, and the way to do this, and I already alluded to this previous in my presentation, namely is just to control the phases of the local oscillator of our measurement system, of our homodynamic detector. So first, what we have to set up, I mean, we have to decide what algorithm to implement, what circuit, and this is then turned into gates. I mean, what gates do we want to implement? I mean, there are these 4 gates that are of relevance for continuous variables. I mean, there's a squeezing gate, there's a rotation gate, and then there's a shearing gate, and then there's a control C gate, a 2-mode gate. So this is a universal gate set for Gaussian computation, and it's also a universal gate set if we use GKP states, as I will come back to later. This can then be implemented just by dialing in phases of our local oscillator. So again, this is our measurement scheme. So we have two homodyne detectors with the control by the measurement angles theta A and theta B, and I'm simply just dialing in different phases at different nodes to implement these gates and thereby the algorithm. Okay. So actually, no, now it works again. So yeah, so it is important to note that we actually performing measurements around the cylinder. So I mean, first we perform measurement of these two nodes, and next we perform measurement of these two nodes, and so on, so forth. So we go around the cylinder when we do the measurement. But he actually, but we encode the input information along the circumference of our cylindrical graph state, and that means that the computation is performed along the cylinder. So we are actually performing the computation in a direction that is orthogonal to the measurement direction. So when we're implementing a gate, for example, along this line here, then we perform a measurement here, and then we have to perform measurement of all the other nodes before we come back to the line along which we perform measurements, or along which we perform computation. So this is important to know. Okay, so we implement a single mode gates first, and the way this is done is to project out lines of 1D cluster states from our 2D cluster states. So as I already alluded to previously, is that we actually have too many entangled links for performing computation in our cluster state. But these entangled links is removed by performing disentangling operations of some of the nodes. So for example, we have performed disentangling operations or measurements on these nodes. So therefore we are losing, or we are getting rid of the entangling links to those cluster states here and those cluster states here. So now we just have these lines of cluster states, and along those lines we can perform 1D computation just through measurements, as I already mentioned. And the input-output relation that we are realizing here can be illustrated simply using the Heisenberg picture. So we have some input states. So this is just a single mode. This is represented by X and P quadratures, and this is then transformed to some output modes. And this is transformed using this symplectic matrix G, which is simply the gate that we are realizing. And there are three different single mode gates, as I already mentioned. So there is the rotation gate, there is the shear gate, and there is a squeezing gate. And they are represented by 2x2 matrices. And we simply measure the different entries of these symplectic matrices representing single mode gates. And this is what you see here. And we can tune the degree of freedom. For example, for the rotation gate, the degree of freedom was a rotation, of course. And here we can rotate our state from -pi to pi. And then we simply measure all entries of this symplectic matrix for this particular transformation. And we see that the measurement and theory agrees extremely well with each other, both for the rotation gate, the shear gate, as well as the squeezing gate. So this is all nice, but we also have a noise contribution, which we should not forget. And this is, of course, what limits the computational depth, because we actually add noise every time we do a computation, every time we do a teleportation. And this is what you see here. So this is a gate noise as a function of different parameters for the rotation gates, shear gate, and squeezing gate. So for the rotation gate, it's a function of the angle theta, which is disappeared on this slide here. And this for the squeezing gate is a function of the squeezing parameter. Okay, so we had 4 dB of squeezing at the input, which is shown by this line here, and then we're simply adding 6 dB of noise in our computation. So we're adding a lot of noise in our teleportation circuit, or in the act of performing a single mode gate. So there's no free lunch. I mean, by performing our computation, we simply add noise. We also implemented 2 mode gates. And in doing this, we established correlations between 2 1D cluster states, so ending up with this 2D cluster state. And in this 2D cluster state, where we had 2 input states, phi1 and phi2, we could perform a 2-mode operation. just by again, just by tuning the the phases of the local oscillators of our measurement system. And this was also successfully implemented, but again, we have a lot of gate noise. So in this case, we had 8 dB of gate noise in every single implementation of the 2-mode gate. And now, because we can implement single mode gates and we can implement 2-mode gates, then we can also set up a circuit. So we simply set up the circuit, and then we figured out, I mean, what do we have to, what type of measurements do we have to perform at each node in our cluster state in order to realize this circuit. So here, this is a circuit with a 3-mode input state. So we have some single mode gates, as shown here. Then we have a 2-mode gate. We have a Fourier gate. We have a lot of identity gates, which are just memory gates. And then we have another 2-mode gate here, and also an inverse Fourier gate here. So we can simply set up different circuits, and this is the symplectic matrix for this particular circuit, and we perform measurement of this symplectic matrix, and we see a nice overlap between theory and experiment. And we also again see that we are adding a lot of gate noise to our state as a result of the teleportation circuit not being ideal. I mean, the reason that we are adding noise in computation is the fact that we don't have infinite squeezing in our cluster state. If each squeeze beam in our cluster state was infinitely squeezed, there will be no gate noise. Okay, so we have to get rid of the gate noise, and this can be done by encoding our information into the right type of qubits. And there are different qubits to choose from in the photonic regimes. I mean, there are multiple different qubits. I mean, the most studied one is the single photon qubit, where you can encode your information into dual rails, or into polarization, or into time pin, and so on and so forth. And you can follow the protocol of Nilda-Flam-Milburn, which is more than 20 years old by now. And this is the approach that has been studied the most throughout the years. But people have realized that it is for error correction, for loss error correction, it might be better to encode your information into higher dimensions. I mean, multi-photon encoding. For example, you can encode your qubit as a cat. A qubit is a superposition of 4 coherent states in phase space, giving rise to this cat qubit. And error correction has actually already been demonstrated on a cat qubit in the microwave regime using superconducting microwave circuits. It has not yet been demonstrated in the optical regime, because there was actually basically no protocol on how to implement error correction in the optical regime. But we came up with a protocol that I will not have time to discuss today. But if you're interested, you can look it up in this archive paper on how to do quantum error correction in the photonic regime with cat state qubits. Another qubit, which is even more robust, is also an old qubit that was proposed also 20 years ago, by the same time as Nilda-Flam-Milburn proposed their computation scheme. There was another computation scheme put forward by those 3 gentlemen, where they proposed to encode our information into what is called DKP qubits, which corresponds. So this is a phase-space picture of the DKP state. So this corresponds to a comb of spikes. Narrow spikes, which are each of which are squeezed both in x and p direction, and these are the projections onto the 2 different axes, the amplitude quadrature and the phase quadrature axis. And we simply see that it simply corresponds to a comb of squeezed states. So it's a superposition of squeezed states that gives you this DKP state. And this DKP state, although it's difficult to produce, nobody actually produced this in the photonic regime yet, it has turned out to be a super nice qubit because it will give rise to fault-tolerant universal quantum computing using only Gaussian transformations and Gaussian measurements. So that's the scheme that we have been looking into. Just briefly, I mean, how do you correct errors or loss or noise that is imposed onto the DKP qubit? So this is the DKP qubit, the 2 logical states So the blue state is the logical 0 state of a GKP state, and the logical 1 state is just another GKP state shifted by square root of pi. This is the red state, is the logical 1 state. And now if you add noise to your state, and as I already mentioned in the previous slide, whenever you perform a gate transformation, you will be adding a lot of noise. That means that these different peaks in your GKP state will be broadened. Now the idea is to use error correction, GKP error correction, to narrow these peaks again. I mean, get rid of this continuous noise. And this can actually be done using a teleportation circuit, where the entangled state are they're not two-mode squeeze states as I have introduced in the previous slides, but they are now GKP belt states. And the GKP belt states are produced by taking a GKP resource states and interfering them on a 50-50 beam splitter that will give you a GKP entangled state or GKP belt state. And this GKP belt state is now used to teleport your corrupted input state into an output state. And by doing this teleportation, you can actually you can clean your state, so you can distill or you can purify your state, which is what is shown here. Because I mean, what you're doing in your bell measurement, you're simply measuring the continuous errors that are imposed onto your state. I mean, this broadening is being measured in your homodine detectors, and therefore you can reset this broadening, or you can remove it in a feed-forward loop, and thereby you get back your narrow spikes. However, there's something to pay here. So sometimes you make an error, because sometimes you perform measurements in this red region here, in this red bin, and that means that you believe that what you measure is actually a GKP 1 state, but it was a GKP 0 state, and therefore in your feed-forward loop, you perform a wrong displacement or correction, a wrong displacement, and that means that a bit of the GKP 1 state, logical 1 state, will be popping up here after you're corrected. So that means that you turn or you convert your continuous errors into qubit errors. So you get rid of your continuous variable noise, your continuous error, but you get qubit errors, and therefore you also need quantum error correction coding in order for this to work. A nice thing to note here is that this error correcting scheme that is shown here is also a teleportation circuit, so therefore this can be directly implemented into our cluster state. And this is what is shown here. This is our proposal for fault-tolerant architecture, which is quite similar to our previous setup. So now the difference is that now we're not only coupling in squeezed vacuum states as shown here, but we're also coupling in these GKP states, and these GKP states are coupled in to enable error correction in our cluster state. So whenever we want to implement a gate transformation, then we couple in squeezed vacuum, and whenever we want to correct for errors, we couple in our GKP state into our cluster state. So we have a switch here that is then choosing between these two input states. And then again, we have delay lines, and these delay lines is then setting up a cluster state now in a 3D lattice. So the idea here is now to make a 3D cluster state, and the reason that we want to make a 3D cluster state is that we want to do qubit error correction, and for qubit error correction or topological qubit error correction, as we're considering, we need a surface for encoding our qubit. And this surface takes another dimension. So therefore, we simply want to make a surface for our qubits, and then the last dimension will be used for computation. And that's the reason that we need a 3D cluster state in order to make a fault-tolerant computation. And the idea is to set up a parallel and a time array of parallel entangled two-mode squeeze states. So we have these. So here we have 9 different two-mode squeeze states arranged in a time lattice, and those states are produced in the first part here, right? And now we want to connect these states, for example, in a line to make 1D or to make a one-mode computation, and this is simply done with this beam splitter here. And now, if we want to connect parallel or wires that are parallel to each other, So for example, if I want to couple this node here with this node here, or this node with that node, then we're activating a beam splitter in this last Maxine interferometer here. So by activating one of these beam splitters, we are simply coupling neighboring 1D cluster states. And by doing this, we can also implement two-mode gates in our cluster state, in our 3D cluster state. And because we have this extra dimension, we can also perform qubit error correction. And we have studied this numerically. I mean, what are the logical C and X error rates as a function of the squeezing variance? I mean, the squeezing of the input squeeze states, as well as the squeezing of these ancillary GKP states. So if we are in this region here, I mean, below 12.7 dB, then we are not able to do quantum error correction. So the different colors here correspond to different distances of our surface code, which I will not have time to go into here, but these are different distances of the surface code. And we see that usually when you increase the distance, I mean, going from the blue to the yellow, then the qubit error correction shall be better and better. So we are introducing less and less errors. But this is not what happens in this region here. So here we are actually adding more and more errors if we increase the distance of our surface code. But if we now go into this region here, then the opposite happens. So now if we increase the distance, we have lower and lower errors in our computation. And this is therefore the fault-tolerant regime. And to get into this regime, we need more than 12.7 dB of squeezing in our input state and in our GKP states. So this is good news that this is still a big challenge to generate 12.7 dB of squeezing, also GKP state. But it's but if we can do this, then the rest is super simple, because consisting just of Gaussian transformations and high efficiency homodyne detection. Okay, so I also want to say a few words about the generation of GKP states. This is, as I mentioned already, has not been generated yet, but we have a scheme on how to do this, and I will not go through this because I have already been spending too much time, but I encourage you to look up this work. It was put on the archive recently. Okay, so just summarizing. So I have introduced you to cluster state quantum computation based on continuous variables. I have mentioned how we in our lab have produced a 2D cluster state, how we have implemented quantum computational gates through projective homodyne measurements. I briefly and very quickly introduced you to a fault-tolerant architecture of continuous variable quantum computing. And then I did not have time to discuss a new scheme for generating GKP states, but again, I encourage you to look up our reference. And with this, I would like to acknowledge my research group, which is behind most of this work, but I should, of course, again, highlight the lead author of the cluster state work, which is done by Mikkel, who is standing right here, and also a lot of the theory, in particular the theory on GKP state generation, was done by Jacob, who is just behind here. Okay, thank you so much for listening to my talk.
Thank you. There are lots of questions, so I would like to ask some of you to unmute yourself and ask the question directly, unless you want me to read it. I guess I still do not know some, because you have acronyms for your chat. So perhaps you might want to unmute. Oh, okay. He's saying that not convenient to talk. Okay. So so the first question he asked was, why beam splitter can entangle two squeeze states? These are elementary questions. I hope you can answer. Does each measurement involve one additional squeeze state in gate teleportation? And then there is another question. V1 and V2 are entangled. So for V2 and V3, and V3 and V4, So does this give an entanglement between V1 and V4? So I'm not sure which slide he's referring to when he's talking about it. But maybe you want to answer the simple one. Why beam splitters can entangle to squeeze states? Actually, squeeze states are already entangled.
Yeah, so I mean that's true. I mean, a squeeze state is often a multimode state which is already entangled. So you have entanglement between different frequency components in a squeeze state. But this is not the type of entanglement we are making use of here. Yeah, so I mean, so the way to produce entanglement in a beam splitter is shown here again. So you have one squeeze beam which is squeezed along the amplitude quadrature, and you have another squeeze beam that is squeezed along the phase quadrature, and they interfere on a 50-50 beam splitter. And you can imagine that what comes out is a very noisy state. You're simply mixing these two in phase space, and since you have anti-squeezing in this direction, anti-squeezing in that direction, then what you get out here is something which is very noisy. So you have anti-squeezing in both directions. But this noise is perfectly correlated to the noise down here, and this is simply due to the fact that that we have squeezing in that state. So we have squeezing in the amplitude quadrature here, so that's why we have amplitude quadrature correlation between those two modes. And because we have squeezing in the phase quadrature of this mode here, that means we have phase quadrature correlation between those modes, or actually anti-correlation between those two modes. And the correlations anti-correlation comes from the fact that you have a phase shift in your beam splitter. Yeah.
Right. Actually, he has another very nice question. So maybe I'll ask that first. Xanadu has brought up a blueprint to use hybrid scheme of the GKP state and squeeze state as input to implement quantum computation. How do you think about the blueprint? Is this hybrid scheme? Okay.
So this is work that is quite related to our proposal here. So in there, let me just go back here. Yeah. Yes, I mean, first of all, the blueprint proposed by Xanadu is based on spatial multiplexing and not time multiplexing as our proposal here. But otherwise is strongly related. I mean, they also use GKP states. I mean what in their proposal they actually assume a cluster state only consisting of GKP states. So you have in all nodes you have GKP states which are entangled. So that means that you don't necessarily have squeezing at the input here. So all the gate transformations are also performed using GKP states as a resource. So I mean, this is the ideal version of their proposal, and this gives actually a better threshold, because using GKP states in your gate transformation will add less noise than using squeeze states. But then they also, they're also aware of the fact, as we are all of us, that it's difficult to generate GKP states. And the day where we will be implementing or generating GKP states, then it will probably be done probabilistically. So maybe you can generate GKP state with a success rate of 90%. So, and what do you then do when you fail that last 10%? And then you can actually, in those cases, you can then inject squeeze states, because squeeze states you can easily generate. So this 10% of the time where the GKP state is failing, they inject squeeze states, for example, and then they calculate the fault tolerance threshold for this. So that they simply take into account the fact that the source of GKP state is probabilistic. So this is an idea that they put forward, that we also used in our proposal here. But otherwise, I mean, it is strongly related. I mean, the main difference is that they assume GKP states for gate transformations, whereas in our proposal we assume squeeze states for the gate transformation.
So, Nilkan, do you want to, Nilkan Kundu, would you like to ask a question yourself? Unmute yourself.
Yeah, so basically I want to understand what is the difference of this continuous variable photonic quantum computing with what was published in USTC. So why is that system not scalable and this one is scalable?
Yeah, so I mean, the reason that, let me go back to their experiment. So the reason that this is not scalable is the fact that they're using free space optics. So I mean, you can see that the setup here is massive, right? You have, each mode into a linear network is a squeeze state, and this squeeze state is produced using a free space squeeze light source, and a free space squeeze light source is takes up the size of 5 by 5 by 5 centimeter, so it has a certain size. And now imagine that you want to have 1 million modes, 1 million squeeze states into your circuit, which you will need for fault-tolerant universal quantum computing. So this will simply take up too much space. So that's why I believe it's not scalable. Of course, I mean, then you can go to integrated circuits, and this is also what many groups are looking into, including Xanadu. So I mean, can you do this Gaussian boson sampling or universal quantum computing in photonic chips? Then it suddenly becomes scalable. But then we need to refine the development of these photonic chips first.
Yep, great, thanks. And there's also a question by YT Lee. You want to unmute yourself and ask? He's asking about since they have built a cluster state, why do you need a control Z gate?
Yes, so I mean, in order to perform universal quantum computing, we need to implement. I don't know what I have a slide of this, probably not. I mean, we need to implement 3 single mode gates and a single 2-mode gate. I mean, this has been proven. This is like a theorem. I mean, you have to be able to generate or to perform gate operation between 2 modes. I mean, a 2-mode gate. And this you need to do no matter whether it's a gate-based model or it's a measurement-based model. But once you can implement those 4 gates, these Gaussian gates on GKP states, I mean, then you have a universal set of gates. But you definitely need to be able to implement gates between 2 modes or more.
So this is just mainly to do to show that you can do universal quantum computing. At least simple.
So say again, sorry?
It's just to show that you have achieved universal quantum computation.
Yeah.
At least to demonstrate that. Yeah.
Yeah, exactly.
All right. Any other questions from the audience? Please ask. Unmute yourself. Feel free to ask. There's a question on what's the difference between a shear gate and a squeeze gate.
Yeah, that's a good question. So so we have, I'm not sure what I have a picture of it, but okay. So, but I mean, the squeezing gate is easy to understand, because I mean that it just squeezes your state along a certain quadrature. So this is what you see here. So this is R is actually the squeezing parameter, and e to the minus r is just, I mean, the variance that you attain after squeezing. So this means this is the squeezing variance, this is the anti-squeezing variance. So you simply squeeze your state in phase space. What the shear gate is doing, and I should also mention that I didn't mention this in my talk, that when we are implementing this gate, the shear gate, then we also at the same time implement a Fourier gate. So we cannot in our teleportation circuit, we cannot solely implement shear gate. So it always combined with a Fourier gate, but this Fourier gate can be then removed later on in the circuit. But the shear gate is a gate that rotates your state and squeezes it at the same time. So you rotate your state in phase space, and at the same time you simply squeeze your state. So this is a shear gate.
Right, Wanling, you want to ask the question yourself?
Yeah, I'd like to check, is the photonic platform the only QV system to realize the squeeze state or the GKV state? And are there some unique advantage for the photonic platform to do this task?
No, it's actually, that's a good question. So, I mean, the DKP state is very difficult to realize on a photonic platform, and nobody did it so far. But I know there are a number of groups looking into it, working on it. But the GKP state has been produced on other platforms. For example, on a microwave platform in superconducting electronics. I mean, superconducting cavities using strong nonlinearities.
It's by Michel Devon.
Exactly, the group at Yale have produced DKP states, and I think they had a new paper on the archive last week where they demonstrated really beautiful demonstrations of the generation of DKP states. And you can also generate DKP states in the phononic mode of degree of freedom of ions. I mean, coupling the phononic degree of freedom to the spin degree of freedom, you can actually generate quite nice DKP states in these ions, which has been demonstrated by Jonathan Holm from Switzerland. So I mean, they have generated GKP states, but they have issues with the scalability. So they cannot scale up the system as we can easily do in the photonic systems. Yeah. So there's always a trade-off.
Thank you. Any other questions from the audience?
Hi.
Yes.
Thanks for the talk. I'm Jonathan. Yeah, I just like to ask. Maybe it's a silly question, but from quantum optics, what I understand is that the general form of a squeeze state, right? They have both the displacement operator and the squeeze operator that act on a vacuum. So I'm wondering, in this setup, are you also able to implement the displacement operator?
I mean, whether we're able to implement the displacement operation?
Yes, displacement operation. Yes.
Yeah. Okay. Yeah. So so we actually do this in every single teleportation implementation. So this I also did not add here. So this is the transformation that I discussed during my talk. So this is the actual gate transformation. This is the noise addition, but there's actually another term here that I didn't mention to you. This is a displacement term that we can tune and control. So the actual displacement is actually easy to tune and implement, but we don't need this. We don't need this for computation. So it's actually, we actually need to get rid of it, and that's why I simply removed it here. And the way that we are getting rid of this experimentally is just in post processing. You don't have to do it. I mean, in real time. I mean, optical in real time, but you can simply do this in the post processing of the photocurrents of the data in your computer afterwards.
I see.
This is easy to get rid of. Yeah.
I see. Thanks.
Right. Any other questions to ask? I think Ulrik has done a wonderful job of explaining a lot of details. I'm quite sure some of you. Yeah. Go on.
Could you tell something about the GKB state generation?
Yeah, sure. So let me just find the. Yeah. Okay. So what we propose here is to use a cavity QED for generating a GKP state. So we have a cavity, high finesse cavity, and in that cavity we place a single emitter or a free level system. It can be an atom or solid state system. inside our high finesse cavity. And then the idea is to and then you can prepare this 3-level system either in one of the 2 spin states, the spin up or spin down state, which are the nodes 0 and 1. So there's an optical transition to the excited state up here. But you can prepare this in the 1 state or the 0 state, so spin up or spin down state. And then you inject light onto your cavity. So in our case, we want to inject squeeze light. And then depending on, and this light will then be reflected off the cavity. And now depending on whether the state of the atom is initialized in the 1 state or the 0 state, we impose a phase shift onto our reflected beam. So if it's in the 1 state, there is no phase shift. If it's in the 0 state, there is a phase shift of pi. So now imagine that you prepare this in a superposition of 0 and 1, then the reflected beam will experience a superposition of a 0 phase shift and pi phase shift. And that gives rise to a superposition state. So if we inject a squeeze state, then we simply end up with a superposition of 2 squeeze states. And this is what is shown here. This is a squeeze state, the wave function of a squeeze state. Then we have to displace it. And then after interacting with the atom and reflection, we get a superposition of a squeeze state. And you can see this is already going towards a GKP state. So now if we re-inject this state, so this, or first we perform a displacement and then we re-inject it into our cavity QED system, then we get a superposition state consisting of 4 peaks. And then we simply can continue this interaction, and therefore we are building up a superposition of many different squeeze states, which is a GKP state. But a better approach is actually to stop the process here. So just to create a superposition of 2 squeeze states. And this is definitely doable today. I mean, there has been an experiment from the group of Gerempe where he produced a catch state, a superposition of 2 coherent states using such a system. So now this has to be upgraded, this experiment, to produce a superposition of 2 squeeze states. And now by doing this in 4 different modes, so you should imagine that you have 4 different cavity QED systems here, and then you interfere them in a linear network, and you do homodyne detection to conditionally prepare the output mode in a DKP state. So this is a way of breeding or amplifying a DKP state using a resource of squeezed superposition states. So if the cooperativity factor or the internal cooperativity factor of our cavity QED system is 200, and the internal cooperativity factor is defined by the standard cooperativity divided by 1 minus the escape efficiency. So if you have a very large escape efficiency of your cavity, then you can easily get a very large cooperativity. So cooperativity of 200 has been realized experimentally today. And using such a system, then you can get a GKP state that looks like this, where each peak will be squeezed by 5 dB. If you now boost your cooperativity, internal cooperativity to 2000, which is not feasible today, but could be feasible in the near future, and you're using this linear network, then you can make such a GKP state here, which is squeezed by 11 dB, which is almost at the fault-tolerant level. Yeah, so this could be a way to go to produce a deterministic DKP state. I mean, there are of course also ways of generating DKP state probabilistically, but this one here is deterministic. Okay. I hope that answered your question.
I have also another question. In the generation we are 2D cluster states, and there are too many long bands, and the 2 neighboring bands are linked somehow. Can you explain it more detailedly?
Could you ask the question again? I didn't get it.
The question is, in the 2D cluster state generation, and in the cylinder, there are many long bands, if I can call it. There are 2 bands. The 2 neighboring bands are linked or entangled.
Yeah. Yeah. So what you're saying that there are too many connections, or
Yes, how they are connected.
Yeah, so let me just go back to our cluster state. Yeah, here. Yeah, so I mean, we have many connections. So I mean, you can see that this node here is entangled to many other nodes. I mean, all the links here represent correlations between the different nodes. And this is the way that we are producing our cluster state yields all these connections, all these correlations. But we don't need those correlations, all these correlations, for realizing our gates, our computations. So so therefore we can redistribute these links through measurements, and this is exactly what we do here. For example, when we implement our single mode gate. So here you can see there are much less connections, and all the connections have now been lost. I mean, for example, we perform measurement of these nodes here, and these measurements are disentangling measurements. So we simply disentangle all these nodes with the other nodes, and we end up with only these links here. And these are the links that we need for implementing our single mode gates. So yeah, I mean, we have too many links, we have too many correlations in our cluster state, but they can be removed through proper measurements.
Okay, thank you. And also another question is the gate teleportation involving a squeezed state? Does that mean that each qubit will be used a different squeezed state as a reference signal to implement the gate teleportation, or just use a common one?
So you're saying, so if we're teleporting a squeeze states?
Yes.
I think I didn't get your question. Maybe you can try to repeat.
I mean, you have an input, right? And then
yeah. Yes. Yeah, so I mean, so you're asking about the input states here.
Yes.
Yeah. Yes. So I mean, ideally, I mean, those input states should be GKP states. I mean, if we want to do universal fault-tolerant computing, but in this realization here, we did not have qubits at the input. Okay, so yeah, so I mean these input states here should be qubits, but in our realizations they were just, I mean, probing states. I mean, probing the transformations. And the way we did this, I also did not explain this in my talk, but this was actually an EPR state that we send in here, or one half of an EPR state, and then we transformed the one half of the EPR state through our cluster state, and then we looked at the correlations between the transform state and the remaining mode, and thereby we could verify the computational scheme. But ideally, there should be qubits or GKP qubits. It could also be squeeze states. So I mean, you could also implement the Gaussian boson sampler in the cluster state, and then this should just be squeeze states at the input.
Okay, thank you. I have another question. Thank you.
Welcome.
Any other questions, if I may ask? If not, I think we're getting very late in Singapore. We're getting for dinner, and Ulrik is trying to go for lunch. And so perhaps you can ask Ulrik directly if you have any further questions, and end this session. Let's thank Ulrik for his wonderful talk today. It's very insightful, and it certainly gives us a lot of motivation towards learning continuous variable quantum computing. Thank you.
Thank you. Thanks for the invitation again.
Yeah.
And thank you for listening.
Let me give you a clap.
Thank you.
Thank you.
Thank you.